All right, we're going to take the expression that allows us to compute compounded interest, and we're going to do a problem with it. So there's the equation. The problem is $12,000 invested at 9%, and it's going to be compounded quarterly over 5 years. So see if you can plug in the values where they go. And it turns out the amount is 12. We're going to find out the amount, and it's going to put in the principal, which you started with, 12,000. 1 plus R is the rate of interest in decimals, divided by the number of times it's compounded per year. It's quarterly, gives us a 4. Raised to the n, there's 4 again, times t, time in years. So if you plug that in your calculator, you'll see that you get that much. Let's see how much more you get if you compound it not 4 times a year, but continuously compounding. So same amounts, same amount of time. So plugging in the amounts, A equals P e to the RT, we get principal E raised to the 0.09 times 5. And surprisingly, the amount turns out to be $18,819.75. So granted it is more, but it's not even like $100 more. So you can see how that actually works out. I'd like you to try a couple of these for your assignment tonight, and I've got them over here. Alright, so here's a little chart that you're going to do for 2 problems. Number 53 is the principals given, the rate of interest, and the time. And as the directions say, complete the chart, taking the balance and finding the balance A for P dollars invested at rate R for T years, compounding n times per year. And the n is this number in the chart. So if we have 1 time per year, 2 times, 4 times, 12 times, 365 times, and continuously. So I want you to do that for number 53 and number 55. So you'll have these answers. You'll have 1, 2, 3, 4, 5, 6 answers for number 53 and 6 answers for number 55. So I would like you to try that. Let's see what you could also do. These 2 problems where we take this chart and we're going to invest $12,000. The rate as stated, 4% for the first one for T years, and the years are enlisted here. These are all compounded continuously, so it's a PERT question. So if you would do that for different amounts of time and see how that changes for number 57 and for number 59. So with those, I will check those with you tomorrow. And let's see if I have any time left. I think I do. There's one other expression I would like to show you, where you can use E. And that is in an example like radioactive decay. So if we start with a radioactive substance, suppose we start with some amount of radioactive substance, and say it starts with 10. Well, over time it starts to get less and less radioactive. And this is the equation that we're going to use. And you'll notice it's not a natural logarithm. It's not a natural base. There's no e in this expression. It's just an exponential. So the unknown is in the exponent. So this is actually the equation that corresponds to the atomic accident where an atomic power plant exploded in 1986 in Chernobyl, Russia. So I was wondering, how safe is it? Can we move back? How much now? How much plutonium or whatever the radioactive material, how much of it is there now? Is it safe to go back? So we're going to say that T is the difference in years, the number of years since 1986. So you're going to have to take the year 2016 now and subtract 1986 and plug in that for T and calculate how much there was. So if we start it with 10, I'm not sure if it was pounds. Let's say it was 10 pounds of radioactive material. How much is there left now? So that's the amount that was spread over that area. How much decay? How much has there been much decay? So go ahead and plug that number in and find out the result. All right, we will take this up tomorrow, and I hope that this recorded and that I get it up successfully. You guys have a great evening. Till tomorrow.